Hello everyone, thanks for coming to Week 8's review, Probability Concepts for Actuarial Mathematics. So in this week, we introduced many important probability theory concepts that we will use. First, we introduced the risk measures. The definition of the risk measure is a function rho that map all variable loss random variable to a real value. We also have the coherent risk measure, which satisfies the following properties: subadditivity, monotonicity, positive homogeneity, and translation invariance. Subadditivity means that rho of x plus y is smaller or equal than rho x plus rho y. Monotonicity means that for two random variables x, which is not larger or equal than y, rho x is also larger or equal than y. Positive homogeneity is that if we have a random variable x and a positive constant c, rho of c times x is c times rho of x. Translation invariance is for a random variable x and a constant c, rho of x plus c is c plus rho of x. So this is important in actuarial calculations to use a coherent risk measure. An example would be the standard deviation risk measure. For a random variable x, we define rho of x to be the expectation plus k times the square root of the variance of x, which is also the standard deviation. So here k is a constant. We have a very special class of random variables called the parametric distribution PD. It's composed of a set of random variables, each of which can be determined by several parameters, and the number of parameters is fixed definite. So instead of identifying the whole distribution, we can get the distribution of each random variable in that set by several parameters. An example would be the normal distribution, where we only need to determine the mean and the variance of each random variable to get the whole probability density distribution. The scale distribution is another special class within the parametric distribution. Its definition is that if for any x, random x belongs to the PD, Cx also belongs to PD. C is a constant, which is larger than 0. A scale parameter is a parameter such that if Cx gets this parameter multiplied by C but all other parameters unchanged, then this parameter is a scale parameter. An example would be the exponential distribution. So if a random variable y obeys the exponential distribution with the parameter theta, and x is cy, then x obeys the exponential distribution with the parameter c times theta. We also have the parametric distribution family. It's just a family of the probability density function of the parametric distribution. In order to generate new random variables, sometimes we can perform transformation of current random variables. This is commonly used in actuarial mathematics calculations. First, we introduce multiplication for a random variable x and a constant theta larger than 0. We can define y to be theta or x. So the cumulative density distribution of y is fx of y over theta. We can also raise to a power for a random variable x, which is usually positive. Y is x to the power 1 over tau. So the CDF of yf, y of y is fx of y to the power tau. Exponentation, we let y to be e to the power of x. X is a random variable, so fy of y is fx of log y. We have mixing for a group of random variables xi. This group is finite and has finite many random variables. We can define the CDF of y, fy of y to be the summation of ai times fxi or y. Here, the summation of the coefficients is 1 and they should be non-negative. We also have the mixture distribution, so it's a continuous version of the mixing because now we have a parameter lambda and fx of x conditioned on lambda can be seen as xi, but here the parameter can be taken from in a continuous space. An example would be the linear exponential family. So here theta is the parameter and fx of x conditioned on theta is px times e to the power rx times x over q e to the power r theta times x divided by q of theta. So it's often used to generate the mixture distribution. Thanks for listening.